Namaste, my friend, and welcome back to NEET Physics with Typical Monk. This is Class 5, and today we meet one of the most beautiful ideas in all of physics: energy. Sit with a small truth for a moment. When you push a box across a floor, you spend effort, and that effort does not vanish. It becomes motion, or heat, or stored energy waiting to be released. Physics gives that traded effort a name: work. And the deepest promise of this chapter is simple. Energy is never created and never destroyed, only handed from one form to another. When Rhea first understood this, every collision problem, every ramp, every spring suddenly became the same problem told in different clothes. Today, one idea at a time, we learn to follow the energy. Take a slow breath. Let us begin. So what will you carry home from today's class? First, work done by a constant force and by a variable force, and the lovely fact that work is just the area under the force graph. Second, the work-energy theorem, that the net work done on a body equals the change in its kinetic energy. Third, the conservation of mechanical energy and power, how fast that work is being done. Fourth, collisions, elastic and inelastic, and the coefficient of restitution that tells them apart. And fifth, the NEET drills, assertion and reason, match the column, and a full work collision numerical. So that everything you learn today, you can also score with. Ready? One idea at a time. Let us begin with a word that means something very precise here. In physics, work is done only when a force moves its point of application through a distance. Holding a heavy bag still, no matter how tired your arm, is zero work, because nothing moves in the direction of the force. Work needs both a force and a displacement, and only the part of the force along the motion counts. Work equals force times displacement times the cosine of the angle between them. When the force and the motion point the same way, the cosine is 1, and the work is greatest. When the force is at a right angle to the motion, the cosine is 0, and the work is 0. This is why the Earth's gravity does no work on a satellite going round in a circle. And work can be negative. Friction always opposes the motion, so the angle is a straight 180 degrees. The cosine is -1, and friction's work is negative. It quietly drains energy out of the body. Arjun forgot that minus sign for months. The day he remembered it, his ramp problems came clean. Now look at this graph carefully, because it is how a physicist sees work itself. For a constant force, work is simply force times displacement. Draw force on the vertical axis and displacement on the horizontal, and the work is a plain rectangle. But most real forces change as you move. A spring pulls harder the more you stretch it. For a variable force, the work is the area under the force displacement curve, whatever its shape. Think of it as slicing the area into thin, vertical strips. Each strip is a nearly constant force times a tiny displacement, a sliver of work. Add up all the slivers and you have the total work. That adding up is exactly what an integral does. And when the force turns around and points backward, the curve dips below the axis. That area counts as negative work, energy taken out of the body. Priya learned to read this graph like a story of energy flowing in and out. Now, here is the bridge from force to speed, the work-energy theorem. First, kinetic energy is the energy a body has because it is moving. It equals 1/2 mv squared. A faster body, or a heavier one, carries more of it. Second, and this is the heart of the chapter, the net work done on a body equals the change in its kinetic energy. Every joule of net work becomes a joule of motion. So positive net work speeds a body up and negative net work slows it down. A braking car does negative work on itself through friction, and its kinetic energy falls to 0. And the quiet beauty is this: the theorem holds for any force at all, constant or variable or a whole tangle of them together. You never need to know the details of the force, only the total work. That is why NEET loves it. Time to solve a full NEET numerical together, slowly, the monk's way. A body of 2 kilograms moving at 6 meters per second strikes a 4-kilogram body sitting at rest. They stick together, a perfectly inelastic collision. We want their common speed afterwards. Step 1. Write down what is given. Mass 1 is 2 kilograms at 6 meters per second. Mass 2 is 4 kilograms at rest. Never skip writing the given data. Half of Rohan's early mistakes vanished the day he started this. Step 2. Recall the law. In every collision, whatever the type, the total momentum is conserved. Total momentum before the collision equals total momentum after. Step 3. The momentum before. It is 2 times 6 plus 4 times 0, which gives 12 kg/meter per second. Step 4. After the collision they stick, so the combined mass is 6 kilograms, all moving together at one common speed v. Step 5. The answer. 6 times v equals 12. So v is 2 meters per second. Notice the twist. Kinetic energy is lost here, turned into heat and deformation. But momentum is not. That single idea, momentum always survives, solves nearly every collision NEET can ask. Let us make the grand law permanent, because NEET tests it again and again. Picture a ball at the top of a smooth curved track, held still. It is not moving, so all its energy is potential. Mass times g times the height h. Now let it go. As it slides down, that height shrinks and the lost potential energy reappears as kinetic energy, 1/2 mv squared. Higher speed, lower height. On a frictionless track, the total potential plus kinetic stays exactly constant from top to bottom. Energy is never lost. It is only traded from one form to the other. And a spring stores energy the very same way. When you compress or stretch it by an amount x, it holds potential energy of 1/2 kx squared, ready to hand back as motion the instant you release it. Ria pictures the total energy as a fixed sum of money. You can move it between pockets, but you can never change the total. Now sit up straight. These 5 lines are what NEET actually asks year after year. 1. Work equals force times displacement times the cosine of the angle between them. Only the component along the motion does work, and a perpendicular force does none. 2. The work energy theorem. Net work equals the change in kinetic energy. Cracks most speed and stopping distance problems in a single line. 3. In every collision momentum is conserved, but kinetic energy is conserved only when the collision is perfectly elastic. This split is the most tested idea in the chapter. 4. The coefficient of restitution measures the bounce. It is 1 for a perfectly elastic collision and 0 for a perfectly inelastic one, where the bodies stick. 5. Power is the rate of doing work. Work divided by time. And the instantaneous power equals force times velocity. NEET loves a quick power calculation. Let us drill the NEET way. Remember the 4 options. Option A, both statements true and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. In a perfectly inelastic collision, kinetic energy is not conserved. Reason, some kinetic energy is converted into heat and deformation. Think, like, Raya. Check each statement alone, then check the link. Is the assertion true? Yes, kinetic energy does fall. Is the reason true? Yes, energy goes into heat and bending. And does the reason explain the assertion? Perfectly. That lost energy is exactly why kinetic energy is not conserved. Both true. Reason explains. Option A. Second one. Assertion. The work done by a centripetal force in uniform circular motion is 0. Reason. The force is always perpendicular to the velocity. Both are true, and here the reason is the very cause. A perpendicular force has a cosine of 0, so it does no work. Both true. Reason explains. Option A. Third one. Assertion. Momentum is not conserved in an inelastic collision. Reason. Kinetic energy is lost in an inelastic collision. Check the reason first. True. Kinetic energy is indeed lost. But the assertion is false. Momentum is always conserved in any collision, elastic or not. The assertion is false. The reason is true. Option D. A quick match now. Say each answer aloud before I reveal it. Kinetic energy, 1/2 mv squared, the energy of motion. Gravitational potential energy, mass times g times height. The energy of position above the ground. Spring potential energy, 1/2 kx squared. The energy stored in a stretched or compressed spring. And instantaneous power, force times velocity. How fast work is being done at this very moment. If all four came to you before the reveal, the energy map is becoming yours. Here's a favorite new NEET format. I will read some statements. You silently count how many are correct. Statement 1. Work done by friction is always negative. Hold your verdict. Statement 2. Kinetic energy is conserved in a perfectly inelastic collision. Think carefully before you answer. Statement 3. Instantaneous power is the dot product of force and velocity. So, how many are correct? Two statements, the first and the third. Friction always opposes motion, so its work is negative, and power truly is force dotted with velocity. But the second one falls. In a perfectly inelastic collision, the body stick and kinetic energy is lost, only momentum is conserved. That single swap is the trap NEET sets, and now you will not fall into it. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. If a force acts on a body, it must work on it. It feels obvious. Force is being applied. Surely work is happening. But here's the truth. A force perpendicular to the motion does zero work. Walking on level ground while carrying a bag does no work against gravity, because gravity points down while you move sideways. Myth 2. In every collision, kinetic energy is conserved. Balls bounce, so surely the energy stays. The truth, only in a perfectly elastic collision is kinetic energy conserved. Momentum is always conserved in every collision, but in an inelastic one, some kinetic energy is lost to heat and deformation. Learn to keep these two conservation ideas apart, and collisions become easy marks. Time to test yourself. Rapid fire. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just the energy map you built today. Question 1. What is the kinetic energy of a 2 kilogram body moving at 3 meters per second? 1/2 times 2 times 3 squared, 9 joules. Question 2. What is the work done by a force acting at 90 degrees to the motion? 0. The cosine of 90 degrees is nothing. Question 3. What is the coefficient of restitution for a perfectly elastic collision? 1. Question 4. What is the power if 100 joules of work is done in 5 seconds? Work over time, 20 watts. And question 5. What is the potential energy of a 2 kilogram mass at a height of 5 meters, taking g as 10? Mass times g times height. 2 times 10 times 5. 100 joules. If those came quickly, you have truly understood today's class. Let us gather the whole class in one slow breath. Work is force times displacement along the motion, and equally the area under the force displacement graph. The work energy theorem says the net work done on a body equals the change in its kinetic energy. On a frictionless path, mechanical energy is conserved. Potential energy trades keenly for kinetic energy. Power is the rate of doing work, and the instantaneous power is force times velocity. In collisions, momentum always survives, but kinetic energy survives only when the collision is perfectly elastic. And next class, we set the whole body spinning, system of particles, and rotational motion, torque, moment of inertia, and the joy of rolling. Do not miss it. And so, my friend, we have followed the energy from start to finish. It may have looked like just work and a few collision rules, but understand this. You have learned one of the deepest laws in all of science. Energy is never created and never destroyed. It is only traded, form to form, pocket to pocket. Every ramp you will ever solve, every spring, every crash, every satellite is just this one law wearing a new costume. Arya, Arjun, Priya, and Ruhan all felt this chapter did the same way you are feeling it now. Be patient with yourself. Tonight, once, slowly, picture the ball rolling down that track and trace the energy as it flows. One idea at a time, you will crack NEET. Of this I am certain. If this class brought you clarity, Subscribe to the channel so the next one finds you. Until then, keep going. I will see you spinning.